Here's another classic type of quadratic function problem, and I haven't worked it out, so I'm not sure what we're going to get here. And this may not be realistic, I just can't tell. But anyway, here's how I stated it. A hotel with 200 rooms has maximum occupancy at $38 per room. In other words, if they charge $38, they'll fill the motel. For each $1 increase, they lose 2 customers. So what price should be charged in order to maximize revenue? All right, so the nice thing about market forces in a capitalistic society is that there are checks and balances on prices getting too high. It turns out that if you charge too much, you lose so much business, it's not worth it. You're actually cutting your throat if you charge too much. If you charge too little, you get lots of business, but you're not charging enough to sustain yourself. That's cutting your throat. There's this medium point here where you maximize your intake, your income or your profit or whatever it is you're trying to do. And so that's it's always a nice thing about when you have free market forces. That happens. Prices tend to settle in about where they ought to be in order to maximize the profit or revenue for the person offering the services, and also distributing the services or goods to the right number of people who can afford it. So anyway, let's see what we can do with this. Now, revenue is the money you take in, and total money, total sales dollars, you might say. So the revenue will be what? It's going to be the price you charge times the number of rooms that you rent. Number of rooms. So, for example, well, up here, if we charge $38, we're going to rent 200 rooms. 38 times 200 is a big number, probably $7,600, and that's the revenue for that evening. All right, so what price should be charged in order to maximize revenue? So I'm going to work with P for price. So let's let P equals to price per room. All right, and what I want to figure out is how many rooms do we rent based upon the price. Now this is, economists would call this the demand. The demand is how much you can sell, or in this case rent. And so we can probably work that out this way. And if they charge a price of $38, I'll put 38 here, then they sell 200 rooms. So here's the demand, which is X rooms. Should I call that X, or maybe I should call that Y? Let me call it Y, because we're used to having Y on this vertical axis. And P will be the price axis. How's that? Yeah, we could say X is price, but I'm going to let P be price. All right, so if we charge $38, we have a demand of 200 rooms. Now, if we raise the price by $1 to $39, then our demand slips to 198. So our price demand curve, which is what this is called, price demand curve, is it's going to look like this, because as we raise the price, the demand or number of rooms we can rent is going to fall. And what is the slope of that line? Well, if I fall 2 rooms per $1 increase, then my slope is going to be -2. My slope is going to be, let me write that over here. The slope is going to be minus 2 rooms per $1 increase. Okay, it's going to be -2. minus 2 rooms per dollar increase. Minus 2. Now what would be the y-intercept? And I realize my graph is nowhere close to scale. But you could also say that, well, according to this, if I lower the price by $1, I should gain 2 customers. So if I was able to, theoretically of course, we don't have more than 200 rooms, but if I could lower the price from $38 down to $0, I'm going to gain 2 customers for every dollar I drop. So that would add, what, 2 times 38 is 76. So my y-intercept would be 276. Alright, so I'm going to write the equation. Y is going to be minus 2p plus 276. And let me just briefly explain this. Some of you are rusty at lines, and you probably haven't seen anybody reason through a line quite like I have here. But let me talk through it again briefly here. If the price is increased by $1, we lose 2 customers. So the slope is minus 2 customers per dollar increase. Minus 2 is my slope. If I were to decrease the price by $38 and take it back to 0, when I go backwards, if this is straight line model would hold, then every time I decrease the price by $1, I should gain 2 more customers. So I gain twice as many customers per dollar decrease. Twice 38 would be 76. And so by the time I got down to 0, I should have, theoretically, 276 customers. I have a feeling they would probably have a lot more customers, but just to get this line drawn, the y-intercept is 276, slope is minus 2, and this is my horizontal variable, normally x, but I call it p this time, and here's my vertical variable y. So there is a linear function describing the demand. Now I'm going to do a little racing here so I can make some room and finish this problem. Alright, I'm going to write the demand up here. The demand is minus, it's y, or minus 2p plus 276. And of course price, we said, was letter P. Revenue is price times demand, or number of rooms. Remember, demand is another word for how many rooms can they rent. So it's price times demand, P times Y, which is P parentheses minus 2P plus 276. So I've translated these words into a function. And lo and behold, guess what? It's a quadratic function. So I'm going to erase this stuff down here so we can finish the problem. But it's a nice problem. I think in your textbook, they tend to give you the demand equation. You don't have to figure it out. But I thought it would be pretty worthwhile to talk through one of these from scratch. I think that would be good for you to see one of these problems, totally from scratch, to see where these things come from.